many of you have watched the movie Fight Club? How many of you remember the last scene? Does today feel like one of those days?
I think it's
Did you watch the news?
we see we hear that both have
It's not.
it's going away. We don't know. Let me show you.
No, I don't remember. I thought you said the rumor.
Oh no. I'm saying that day. That day I feel.
Second set.
Oh.
I like it.
Okay, so before we start, I have two announcements. One is that, contrary to the rumors, there will be a discussion session this afternoon led by Tracy and the second announcement is that on Monday, coming Monday, we're going to reshuffle the lecture a little bit. So we'll have two lectures on Neutrino in the morning, and then one lecture by Nima in the afternoon, and it's just a reordering of the event. Okay, let's. So if you send us that, what? Send us those. Yeah. All right.
Okay, so let me restart again where we sort of picked off, just by summarizing what the old standard model looked like as far as neutrinos are concerned. So what I try to tell you a little bit about is the fact that we knew about three neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. They get these names because when they hit something, the electron neutrino produces an electron, the muon neutrino produces a muon, and the tau neutrino produces a tau. And the theory was such that there were global symmetries associated to all of this. So you can assign quantum numbers to the electron neutrino and the electron, and the muon neutrino and the muon, and the tau neutrino and the tau in such a way that you had some conserved quantity called electron number, muon number, and tau number. Okay, so this is a situation that we had set up before. And when it comes to neutrino properties, neutrinos are interesting particles in the standard model. So they have no color. They don't have any charge. So they only talk to the W and the Z. So they only have weak interactions. That's what makes them very, very hard to study. And nonetheless, of course, we've made a lot of progress in doing lots of neutrino experiments. Even before the large number of neutrino experiments that are going on right now, doing neutrino experiments was a huge deal starting out in the 70s. And the main reason is that neutrinos are a great way of studying, for example, the weak interactions. Because if you want to do a study to understand properties of the weak interactions, if you do experiments with electrons, electrons have the electromagnetic interaction. So to learn stuff about the weak interactions with electrons is challenging in the sense that there are always these electromagnetic interactions that get in the way. If you do an experiment with neutrinos, on the other hand, it's great because there's no electromagnetic interactions. So everything that happens are the weak interactions. And of course, the neutrinos played a big role in understanding things like the structure of nuclei and nucleons as well. So this is what was going on with neutrinos that comes about because of this. Now, there are other more technical things about neutrinos that I want to mention. Of course, the most interesting one was that at least until recently, neutrinos were supposed to have no mass. And this fact came about from a combination of different things. One is, of course, that we hadn't observed any effect of a non-zero neutrino mass, even though we tried in lots of different ways. It also had to do with the fact that the neutrinos only have the weak interactions, and the weak interactions are purely left-handed. So that means, from a field theory point of view, if you say that there's such a thing as a left-handed neutrino field, and this is a biofermion, so it's a chiral field, and you all heard about this, say, in the Standard Model lectures, I'm sure. So the neutrino field is a left-handed chiral field, and from a particle content point of view, the particles that live in this field are a left-handed one, which we call the neutrino, and then there's a right-handed one, come along with positively charged leptons. We have never observed any evidence that this is not correct. Okay, and this is built into our definition of what neutrinos and antineutrinos mean. Okay, so this is what we know, and what's really exciting is the fact that over the last 20 years, we became very, very sure that this is wrong. So there's stuff that's missing. Okay, so this is what I'm going to talk about today, and I will do this in a less historical fashion than I did yesterday, and I'll sort of combine things in lots of different ways. But basically, what we found out is that the stuff that I wrote on the left-hand side is incorrect. Okay, so what we have experimental evidence for is that it's possible to produce a muon neutrino, have it propagate a really long distance, and then have it hit something and produce a tau, for example. Okay, or you can do that with the electron neutrino, and we can have it hit something and produce a muon. Okay, so this is what we've discovered, and it turns out that this only happens if you wait long enough. So if you do it right away, it doesn't happen. So there's sort of what we call a flavor change. As a function of L, which is what we call the baseline. And the way you want to think about this is it's how far the neutrinos travel. And this is a really big deal. Okay? So this is what I want to try to talk about today. And I'll hopefully get to the point of understanding how we explain this particular phenomenon. All right. So this is a very old problem that started out in the 60s, and that's what I want to start talking about. So the first thing that happened was people started to understand solar neutrinos. And this is a really exciting, very important topic that also started off, I don't know, in the 30s and the 40s, or actually started off way before, when people try to understand how the sun works. And you've probably heard stories about this. Even before the 20th century, people were very puzzled about the fact that the sun was emitting a ridiculous amount of energy. And they didn't know where the energy was coming from. It's a puzzle. I mean, the sun radiates a ridiculous amount of energy, and somehow it keeps on doing that. And if you've never thought about this, it's pretty weird. Okay, you're emitting this electromagnetic radiation constantly, and you can keep on doing it for billions of years. And people had absolutely no idea how this worked. It's a big thing because it's a very subtle effect, and it requires microscopic physics. Right? It's a nuclear fusion process that takes advantage of the fact that you can change your mass a little bit and convert that into ridiculous amounts of energy, which is kind of how the sun works. And it took a long time for people to get this idea correctly in the details. And there are lots of models that were written down. But the main point is, of course, that the sun burns by solar fusion. So you can take lighter nuclei and you can make bigger ones. And the other thing you want to keep in mind is the sun is very proton rich. So the sun has lots of protons, it doesn't have many neutrons, and has a bunch of electrons to balance out the charge. But because the sun is very proton rich, you can quickly convince yourself that in the process of forming nuclei, you also emit a lot of neutrinos. They're not antineutrinos, they're proper neutrinos. This is kind of the opposite of beta decaying nuclei. Again, the picture you want to have in your mind of a beta decaying nucleus. These are usually nuclei that have too many neutrons in them. So they're happy to convert some neutrons into protons and emit electrons and antineutrinos at the same time. On the flip side, if you have an environment that's very proton rich and you are making nuclei, that means you're converting protons into neutrons. To balance out the charge, you have to make out positrons and neutrinos at the same time to conserve this lepton number law that I was telling you about before. Okay, so that means that the sun, it turns out, is a very, very efficient machine for producing neutrinos. And when people figured out how the sun burns, or they were postulating how the sun burns, this was a big thing that stuck out. And you say, hey, the sun is emitting all of these neutrinos. Wouldn't it be great if we could see them? Right? So that's what people started thinking about how to do. And a couple of very smart, so actually I have a nice plot here. This is a chart of how the sun works. This is a modern version of how we understand the sun working. It mostly works by a PP fusion. That statement is not completely obvious. It turns out that in different astronomical bodies, the dominant fusion chain is not this PP chain, but it can go via carbon burning. There's some stars that are happy to because they have lots of carbon. But this is mostly how the sun works. And as you see, these are all of the nuclear reactions that are happening. There's lots and lots of steps. You probably heard about Big Bang nucleosynthesis. This is a version of that in a very, very different environment. And you're basically making helium, just like people always do. And then there's other stuff that also happens that are very important for neutrino physics, but are not particularly important for the sun. Okay, so this is how the sun works. And we can do a little bit better than that. So I want to show the next plot because that will have the experiments in them. And the idea is not only we can calculate the flux of neutrinos coming from the sun, which is a really high flux. I always forget the numbers, but it's like 1 trillion neutrinos per second going through you every second. It's a large number. Okay. And what's very important, of course, is that we can calculate how many neutrinos are coming from the sun, and we can also calculate what kinds of energies they have. So that's the information that you have in order to construct an experiment to detect these neutrinos. Okay? There are lots of things which are very important. These are relatively or very low energy things. So they will have energies below 10 MeV for the most part. So we're talking about detecting what particle physics people refer to as low energy neutrinos. And the question is, how do you do that? And we've developed over the year lots of different techniques for doing that. And that's included in this plot, which I guess people don't see anymore, but it used to be a very famous plot, 10 years ago. And there are different kinds of experiments people have constructed in order to see these neutrinos. The first one, the oldest one that started taking data in the 60s, is an experiment using chlorine. Okay? So the question is, how do you detect these very low energy neutrinos? There are lots of interesting ideas you can come up with. So first of all, remember, cross-sections are very small. So you need a large amount of something which is going to be your target. Now, neutrinos, you would like to see them by having them hit something. And remember, they only talk via the W and the Z. So if they interact with something via the Z boson at these really, really low energies, the best you can get is that the neutrino will hit something and will make that something recoil. And you probably heard about this from Tali. He probably talked about this neutrino floor for dark matter experiments. That comes from a coherent neutrino nucleus scattering, which actually doesn't have a very tiny cross-section, but it's a really challenging process to observe. Imagine a neutrino comes in, it hits something, and then your nucleus recoils a little bit. And you have to observe that. And we have never observed that ever. even though we've tried, and we're actually building experiments to try to observe this. It's actually kind of ironic that that might be the biggest background for dark matter detection in the future, because it's a physics process we've never measured before, because it's so rare. But nonetheless, that's where we are. Then the other process you can look for is that the neutrino will hit something and it will produce an electron. So now you're kind of in business because you have an electron. But the challenge is, of course, that you are living in this very complicated environment where your electron has to be able to give you a signal. And it's a very low energy electron because the energies that we're talking about are relatively small. So the ideas that people had for how to measure these neutrinos in the beginning were a little bit different from standard ways that particle physics people would think about doing an experiment. And the first one was what's called the Chlorine Experiment. And the idea is you have a neutrino. It would hit a chlorine nucleus. And of course, it has a charge-current interaction. And it produces an electron. And then it produces argon. Okay, so that's the idea. And again, if we had a periodic table in the room, we could confirm that that's actually true. But you produce argon. So what people figured out was, I want to have a scheme where I have a really big detector made out of chlorine. And then these neutrinos are coming in and they're producing argon. And I'm going to see this argon. That's the idea. Okay? It's a great idea because argon is a noble gas. So noble gases will not mix with the environment very well. So they kind of stick out. So if you have a technique for extracting argon out of chlorine, that would get you halfway there. And the other way, of course, is that you have to know that there's argon there. And what's fortunate is when you do this reaction, you actually get some excited state of argon, which decays not very quickly. So you actually have enough time to expose your detector to the solar neutrinos, which is easy because the solar neutrinos are coming in all the time. Then you would take your detector, you would try to get the argon out, and then you'd look for argons decaying there. That's the idea. Okay? So it's a very clever idea. It was followed up by the Gallium experiments. These are experiments from the 90s that use a very similar technique. It turns out that when you hit gallium with a neutrino, you produce germanium. It's also a radioactive version of germanium. And people figured out a way of identifying these germanium atoms inside of some gallium vat, let's say. So that's kind of the idea. Now, these are very, very, very hard experiments. Just from the sheer sort of numbers that you have to work with. And I'm not going to spend too much time on this. This is the Ray Davis experiment. It's also a Nobel Prize winning experiment. And the idea is chlorine is very easy to get. You can go to the store and buy a lot of chlorine. And you can use it for cleaning stuff. So you get a lot of cleaning fluid. You put it inside this gigantic gallon. And then you wait for about a month or so. And then you look for argon there. And the signal that they're looking for, they could do a calculation. They had sort of a handful of atoms per month inside a gigantic tank of chlorine. You know, a gigantic tank, you want to think really big truck that you see driving on the road, tank of chlorine. And you're looking for a few atoms of argon every month. That's the experiment. It's a very hard experiment. It's very unusual for particle physics people, this type of experiment. And it mostly involves a lot of chemistry. And we all know chemistry is very hard. So this is the experiment. They made this measurement, and they made this measurement for about 4 decades or so. And what's really exciting is, first of all, they saw the neutrinos coming from the sun. So everybody was really excited about that. And most importantly, for us, they saw fewer neutrinos than they expected. And again, not just by a little bit, by a lot. You know, they saw about 1/3 of the neutrinos that they expected. And again, historically, most people did not care about this at all for lots of reasons. One is that, and I think the gut reaction of most people who would care is that, hey, you're doing a really hard experiment. You got the answer right to within a factor of 3. I think that's a great result. And of course, there's another problem, which is in calculating these predictions, you have to understand how the sun works in a certain amount of detail. And these calculations are also very hard. The nuclear physics part is a little bit challenging because you have to understand cross-sections of some relatively unusual reactions. So if you go back to this table, a lot of the neutrinos that you're seeing are coming from things like, where are we? Okay, this is beta decay of boron-8. That's not so bad. But you have things like electron capture on beryllium-7 giving you lithium-7. You have some other nuclear reactions there that have rates that we don't understand very well. This is mostly true for the stuff that's in the bottom here. So people also had lots of doubts about the fact that these calculations were very hard. So they also depend on the environment of the sun, and they're all very tricky. This is one type of experiment. And like I said, there's the Gallium experiment. Life started changing qualitatively when the very large water detectors came in. And the idea is that they chose to measure something else. And by the way, if you have a neutrino hitting something in water, you basically have three potential targets. You have hydrogen, you have oxygen, and you have electrons. The oxygen are very unhappy to be hit by neutrinos and give you an electron. And you probably know this very well because the idea is you have to take oxygen, hit it, and turn it into a different nucleus. Oxygen is a very happy nucleus. It doesn't like to be turned into a different nucleus. It's a very tightly bound nucleus. And neutrinos have a hard time hitting protons because of this lepton number conservation. Because when neutrinos hit something, they have to produce electrons. The proton has plus charge, so that means the proton would have to turn into something that has doubly plus charge, and you can't do that at very low energies. So that means that in these big water detectors, the thing you can hit are the electrons. So this is the other thing you can study. This is a very interesting physics process. And it turns out that the big deal is that in these very big water tanks, which were constructed for looking for proton decay, we could see electrons, even relatively low energy electrons. You know, we can see MEV type electrons. And that's the main idea. So that was another way that we could measure the flux of neutrinos coming from the sun. And again, these experiments started out probably in the late 80s, early 90s. The Chlorine Experiment is very old. The Gallium Experiments are also from the 90s. And they're all aimed at detecting neutrinos from the sun. I do want to mention one thing which I should have mentioned yesterday, which is this chlorine detector. The first thing that they did with this detector was to put it next to a nuclear reactor. Okay, so that was a very strong source of anti-neutrinos. And curiously enough, they didn't see anything, which is kind of a big deal because we knew that they weren't supposed to see anything because the nuclear reactor is emitting anti-neutrinos. When an anti-neutrino hits chlorine, it does not produce argon. It produces some other nucleus, which is probably not even allowed by conservation of energy. So this reaction doesn't go. So you're not expected to see anything, and they didn't. There's an interesting rumor, which is probably not completely correct, but I'll tell you anyway. So there's a rumor, this is an experiment done in the US, and there was a rumor that percolated through Europe that they actually had seen something. And that was very mysterious. So that rumor percolated all the way out to the Soviet Union at the time. And then somebody wrote a theory that explained how an anti-neutrino could behave like a neutrino. And actually, they wrote down a model of neutrino-antineutrino oscillations. And it's easy to understand why they would do that, because we know that kaons oscillate. So we have models of KK bar oscillations. So they wrote down this weird model about neutrino-antineutrino oscillations, which had all kinds of problems in it. And eventually that morphed into our understanding of neutrino oscillations today. Instead of doing neutrino-antineutrino oscillations, we do neutrino oscillations amongst the different flavors. And that was a paper by Pontecorvo that apparently was based on a false rumor that the Chlorine Experiment had seen neutrinos from a nuclear reactor, which is also kind of interesting. Okay, so these are the types of experiments that we have. These plots also used to be very famous. You don't see them around anymore. This is supposed to be the results of these measurements. It's a very complicated figure. So what you want to keep in mind is the colored bars are the expectations of how many neutrinos you should see. And the blue measurements are how many neutrinos you actually saw. So if you ignore this particular part of the bar for a second, this picture, the rest of this left-hand side is what was called the solar neutrino puzzle, or the solar neutrino problem, which was that we were seeing fewer neutrinos than we expected. And part of the reason why we did so many experiments was that if you didn't believe this experiment, there were all these other experiments that were also seeing a deficit. So people got very interested in trying to understand what was going on with this experiment. And of course, there are lots of logical possibilities for what's going wrong. One is, of course, that the experiments maybe are all wrong. They've all just screwed up in a coherent way that leads you to believe that you're seeing fewer neutrinos than you should be seeing. That's one logical possibility, and that's why we do lots of experiments. It's very unlikely that they're all wrong because these are all completely different experiments. The second logical possibility is that our understanding of the sun is not as sharp as we thought it was. And maybe these calculations are giving us the wrong flux by an order 1 factor or so. That turned out to be really, really hard to do because of the details of the calculation. And there are very coarse-grained analysis you can do of the calculation that can convince you that having the calculation be very wrong is impossible. Okay? And that has to do with the different colors that show up in this figure. And it basically, if you do a completely agnostic analysis of how to solve the solar neutrino problem by saying that the calculations were wrong, this is kind of informative. Basically, what you can do is to say, hey, maybe the number of these boromate neutrinos is wrong by about a factor of 2 or 3. And that's not very hard to believe, but it's important that it's only a factor of 2 or 3. Okay? So that explains, for example, the water data. And then you have the gallium data. The gallium data has to do with these pp neutrinos. And you can't make all of those go away because they are everything. So that's the flux that you understand very well. So if you wanted to explain the data, there's some intermediate source of neutrinos here that has to be not there. And one culprit was these so-called the Beryllium 7 neutrinos. That was one component. And maybe you said, hey, maybe there's no Beryllium 7 in the sun. Or maybe the Beryllium 7 neutrino flux is really small. And again, we don't know any nuclear physics. So you might believe that that's a logical possibility. You know, maybe somehow that gets quenched in some way that we don't understand. And that's why we have a lot fewer neutrinos than we expect. The problem is these Beryllium 7 neutrinos are produced in this beryllium electron capture reaction. And the boromate neutrinos are produced by this Beryllium 7 proton capture reaction. And it's virtually impossible to believe a world where you can have none of this going on and at least 30% of this going on. This reaction is much harder to do than that one. So just by playing very, very simple games, we knew that the solar model, even if it wasn't perfect, it couldn't be wrong at the level that would explain all these data. So finally, the last hypothesis that you can raise is that maybe neutrinos are wrong, right? Or that the way that we understand neutrino propagation is incorrect. And there are lots of things you can think about. Maybe the neutrinos decay. Maybe the neutrinos get absorbed. So you may have watched the 2012. You know that the neutrino cross-section can change very quickly, only on the planet Earth, but not in the sun. So the idea is that maybe the neutrinos are doing something funny. So one hypothesis that people raised was this flavor-changing hypothesis. It's a very simple hypothesis. You don't need a mechanism for it for now. The idea is, even though the sun only knows how to produce electron neutrinos, imagine that for some reason, by the time they get here, some of those are actually muon and tau neutrinos. Imagine that was going on. That can explain all of this, because all of your experiments are virtually insensitive to mu1 and tau neutrinos. These experiments here, both in gallium and in chlorine, that's right. They only see the electron neutrinos. They don't care about the other flavors. Neutrino electron scattering is actually very interesting because neutrino electron scattering happens for the other flavors as well. However, this cross-section at these types of energies is about 15% of those cross-sections. And that's also easy for you to convince yourself. This is a process that has both neutral currents and charge currents, and this has only the neutral current component. And it turns out that when you do the calculation, this process here is especially suppressed relative to that one. So now you have an opportunity to test this hypothesis, and that's what the SNOW experiment was about. So let me tell you a little bit about the SNOW experiment. It's a heavy water experiment. And again, it's a Nobel Prize winning experiment. So it's a very, very clever experiment. And the idea is if you had a way of detecting a neutrino neutral current reaction, so a pure neutral current process, then that process wouldn't care whether you have a mu1 neutrino, an electron neutrino, or a tau neutrino. They would all contribute in the same way. So what they did is they constructed a big heavy water tank, and they figured out that when a neutrino hits a deuteron, okay, that's the neutron proton bound state, because that's, I don't even know, D is probably not the right letter. When the neutrino hits that bound state, that's a very loosely bound state. That's one of these really important things to know. It plays a big role in Big Bang nucleosynthesis, for example. That it takes a long time to form deuteron because deuteron is very loosely bound, so if you hit it, it kind of breaks apart. And that kind of plays a big role in explaining why Big Bang nucleosynthesis takes a particularly long time to start, because if you want to start producing helium, you have to go through deuteron at some point. Anyway, it doesn't matter. But when this happens here, there's a possibility that this breaks apart this way, and this happens for all kinds of neutrinos. So if you build an experiment with a large amount of deuteron, then this is what happens. And here you have neutrons, and if you have a way of detecting neutrons, then you're in business. So that's what the SNOW experiment was about. It's basically a very big tank of heavy water where you have a lot of deuteron, and they have lots of different ways of detecting neutrons. Okay? The same experiment, of course, can have the electron neutrino can hit, and it can give you an electron and 2 protons. By the way, detecting protons is absolutely hopeless. Okay? You have a low energy proton inside of something, it's lost. You will never ever see it do anything. Neutrons are more interesting. Okay. So this is the other process that they could look for. And finally, they could also look for this reaction that I wrote down before. And like I said, what's exciting about this reaction is that different neutrino flavors participate. And of course, they were very good at looking at electrons. So they could see electrons, and they can also see these neutrons here. So that means that the same experiment can do 3 measurements at once. They can see a physics reaction where only the electron neutrino participates. And then they can see a physics reaction where the electron neutrino participates with a big cross-section, and the mu1 and tau flavors participate with a much smaller cross-section. And then they see another physics process where all neutrinos participate with the same cross-section. So if somehow there were neutrinos arriving from the sun that were behaving as mu1 and tau neutrinos, that experiment could do it. That experiment could test that hypothesis. That's what that experiment was built for, and that's exactly what they did. This is illustrated in this plot in the bar on the very right-hand side. This here is this neutral current measurement. And you see that that's the only measurement where you actually get the right answer. Now, there's a much more impressive plot, which I think is the next one, which is right here. So these are these different measurements made by the SNO experiment. So this is the flux of electron neutrinos coming from the sun. And this is the flux of muon or tau neutrinos coming from the sun. And keep in mind, the sun doesn't know how to produce these guys. But by the time they get here, that's the question that you're asking. And like I said, you can do 3 different kinds of measurements. You can do this purely charged current measurement, this one. It only sees the electron neutrino part of the flux. And you get this really nice red bar over here. And it tells you that the flux of electron neutrinos is this much. Then you can do this scattering off of electrons. And that scattering off of electrons is mostly a measurement of this flux, but it receives a non-trivial contribution from that flux as well. So it gives you a line on this plot which has some angle to it. And you get this bar here, which is this green bar. This error bar is way bigger than that one, because the scattering cross-section off of electrons is way smaller than the scattering cross-sections off of nuclei. But nonetheless, you get this bar, and then you get that one. And then finally, the last result is this blue line over here. So this blue line over here is a neutral current reaction. That's this measurement of neutrons. And if you look at this, you get 3 different lines. They all meet at a point, which is already a non-trivial statement. And they meet at a point which is right over here. And the really impressive result is that what you want to keep in mind is that somehow about 2/3 of all the neutrinos coming from the sun are of the muon and tau flavor. Okay, and this is a very, very unambiguous result. If you're in the sigma business, by now it's kind of like a 10 sigma result. We know that this is happening. And by the way, this dashed line over here gives you the expectations of the standard solar model, that very complicated calculation that was done starting out in the 60s, and is still carried out even today, and the agreement is actually very good. Some will say it's too good. So this is kind of the idea, and that's what told us for sure that somehow it is possible to produce a lot of electron neutrinos in the sun, and by the time they get here, many of them are behaving like muon or tau neutrinos. Okay? So that's the experimental situation, and this was unambiguously resolved. By the way, to be fair, if you only look at the red line and the green line, they do it, yeah. So this is coming from, so I was very fast. So the electron neutrino flux is about 1.5 in these units. And the flux of the other type is about 3.5 in these units. So that's where the factor of 3, very loosely speaking, is coming from. So does that make sense? So, I mean, the only thing I was going to say is that if you just look at the green and the red, they already gave you a lot of the answer. And so even before, so this part of the SNO measurement, the blue line, is the hardest one. And it's the one that you really want to make sure you get it correctly. And they measure that in 3 different ways. So remember, the challenge is to look for neutrons. And they looked for neutrons in 3 different ways. One is that neutron will get captured by something in the heavy water, and then it will emit a gamma ray. So they looked for that. That gamma ray is not very easy to see. So one way of getting around that is that they took the heavy water and they dumped salt into it. So they mixed the salt into it, and the salt had a nucleus that has a very large cross-section for absorbing neutrons and giving you a beefier sort of gamma ray signal. So that's what they did. They put the salt into the detector. They're very scared because they didn't want to have the salt there forever. So they had a very complicated filtration scheme to make sure that the salt would be something that you could get out at the end. So they managed to do that. And then they did the neutron measurement in a 3rd way, which is they built some dedicated neutron detectors that were made out of helium-3. Helium-3 has a gigantic neutron capture cross-section, which you can probably imagine. And so you make these helium counters, which they added onto the inside of their detector. And they use those to measure neutrons as well. So those 3 different techniques were used, and they're all consistent with one another. So this is the SNO experiment, and that's what we learned from them. So let me tell you about a different kind of experiment, which is neutrinos from the atmosphere. And this was the really big deal because this result became very unambiguous before the SNO results came out. And this is also very important. This is the Supercamioconda Experiment. That's the other Nobel Prize for the discovery of neutrino oscillations. And the idea is very simple. So people were, if you try to understand what happens when cosmic rays hit the atmosphere, you produce mostly a bunch of pions. So you have a lot of pions, and the pions decay. And if you have enough time, the muons also decay. And the same thing happens for the other charge as well. So what happens is, as long as you have enough time for the muons to decay, cosmic rays hitting the atmosphere are producing neutrinos all the time. And they produce muon-type neutrinos. There's a bar missing here. They produce muon-type neutrinos, and they also produce electron-type neutrinos. And those are the neutrinos that you can try to measure. And there are lots of predictions you can make. You can make predictions about the total flux. You can make predictions about the energy distribution of the neutrinos. These are all relatively dirty calculations to make because they depend on the flux of cosmic rays hitting the atmosphere. They depend on the atmosphere. So you have to know what your target is, which is the atmosphere. They depend on pion production reactions by hitting cosmic rays off of nitrogen. So it's hard. But there are some relatively robust predictions you can make. And one prediction that you can make is, if you are in a scenario where the energies are relatively low, that means that these muons don't have a lot of energy, which means that they can decay. You expect to get 2 muon-type neutrinos for 1 electron-type neutrino. That's a pretty robust prediction you can make. It does not depend on details of your calculation. Then there's another more impressive prediction you can make, which is the following. So here's the Earth. Here's the atmosphere, not to scale. And here's your detector. Okay? And if you look at neutrinos that come from above, and then you look at neutrinos which are produced in the atmosphere on the other side of the Earth, over here, it turns out, because we live in 3 dimensions, that the flux that you get from below and from above is the same. The only assumption that goes into this is that the flux of cosmic rays is kind of isotropic. This can get screwed up by things like the Earth's magnetic field, but it's screwed up in ways that you can calculate. So it's pretty robust. It's actually really, really robust. So there are 2 robust things you can measure. One is this muon to electron ratio. The other one is this top-down ratio, that you expect the same amount from above and from below. Okay, so that's what people knew about atmospheric neutrinos. It turns out that there were some experiments dedicated to measuring atmospheric neutrinos, for reasons I don't remember right now. And then there were different kind of detectors, which were these really gigantic water tanks. And they started out a while ago, but I think the more famous ones are things like the IMB detector in the United States and the Kamiokonda detector in Japan. And I don't know how much you know about these detectors, but the one I want to remind you of is there's this detector called Kamiokonda. Now, where does it get its name? And unless you're Japanese, so don't say anything if you're Japanese. But so where does this word come from? So Kamioka is the name of a mine or a mountain in Japan, and that's this part I don't know, but I know it's Kamioka is the name of the place, and that's where the detector is. And then you have this NDE, and NDE stands for Nucleon Decay Experiment. So this is a very big proton decay experiment. So people were looking for proton decay. As you might remember, proton decay was a big business in the 1980s because of grand unified theories. Right? So people came up with these grand unified theories, and they were really excited because you made a prediction that the proton had to decay and you could calculate the lifetime. And then a supersymmetry came along, and it made the lifetime be different. And people got very excited about that. So these Nucleon decay experiments were built. And again, you know all about these experiments. Did anybody talk about Nucleon decay experiments? There's not much to say. It's just that you want a large amount of stuff, and then you wait for a proton to decay. The bound on the proton lifetime is like 10 to the 30-something years. So you need a lot of protons. And you need to wait a really long time. And you better not have any background. Because any background is the death of you. Right? Because, you know, if there's a background, even if it's a ridiculously rare background, you have to fight it off against proton decay, which has a ridiculously long lifetime. So the idea is you took a large amount of material, so it can't be very expensive. So water is a good material because it's not very expensive, and it's something that you can make very clean, very pure. It's hard, but you can do it. And then you put it as deep underground as possible in order to get rid of as much background as you can think of. So that's what these detectors were for. They were built for looking for proton decay. And then somebody reminded themselves that, hey, there are these atmospheric neutrinos. They are a background. And they're a background you can't shield because they're neutrinos. And if you make your detector bigger, you will get more of those events. So we need to understand that background as much as we can in order to make sure that they don't prevent us from looking for proton decay. And that's what these experiments were built for, and that's why they were interested in the atmospheric neutrinos. So lo and behold, when they make the measurement, in particular, this was the prediction that I told you about. The flux from above and below better be 1. And when you measure that, the answer is not 1. The answer is a half. And this is a really robust prediction. You're not going to get that off by a factor of 2. You know, the Earth's magnetic field can give you some corrections that you can work out, but it's not going to be a factor of 2. And this is the very, very, very famous Supercamioconda result. The Camioconda experiment already had this result before, but the error bar was very big, and they weren't very sure, so they didn't make a big deal out of it. They did write lots of papers, but it was this result here that convinced everybody that there was something going on in a very major way. Okay? Now, they can do way better than that. They can measure all different kinds of things. So this is a result of what they measure. And let me just tell you what these plots mean. So what they do is that they split out their data sample in different categories. So the categories that we care about is they have things that look like electrons. They're very good at separating electrons from muons. They can tell muons from electrons. So they have electron events. They have muon events. Then they have low energy muon events and high energy muon events. And then they have another category of events which are neutrino events where the neutrino hits something outside of the detector, but a muon goes into your detector from the outside. And they mostly do that with events that come from below. So basically, you have your detector here. So here's your detector. And you see a muon coming in from over here. Okay? And you know for sure that there's no way that's a muon that was produced in the atmosphere, because the atmosphere is up there. Okay? So these events, they also count, and those only happen for very high energy neutrinos. So anyway, so they have all these different samples, and then they make a measurement of the flux as a function of the direction of the electron or the muon that they see. And that's this cosine of theta. And all that we want to see is the fact that, so when cosine of theta equals 1, these are neutrinos that are coming from above you. And when cosine of theta is -1, these are neutrinos that are coming from the other side of the Earth. Okay? So this is the plot. What we really care about are the data points, and we care about the solid line. So the data points are the observations, and the solid line are the predictions. Okay? So if you stare at this, you notice that for the electron neutrinos, everything works more or less very well. Okay? On the other hand, for the muon neutrinos, it doesn't work very well at all. So you notice that this plot here is in disagreement. This plot here also is in disagreement. This one here also doesn't work. This one here also doesn't work. These two here actually work pretty well. So that means you have an effect that says that you don't understand what the muon neutrinos are doing, and that effect depends on the neutrino energy, and it also depends on how far the neutrinos are propagating. Okay, so again, neutrinos coming from above, those work pretty well, and neutrinos coming from below don't work very well at all. We're missing most of those. We're missing about half of them. So this is a very, very, very exciting result because you're very sure that the measurements are correct. The observable that you're measuring is a very robust observable. So even if you don't understand your flux very well, there's no way that a miscalculation can do any of this. So the only way that this can be explained is by saying that the neutrinos are doing something. And whatever it is that they're doing depends on the energy, and it depends on the baseline. It depends on how much they've traveled. Now, why is this very important? Because now your job is to come up with a hypothesis of what's going on. And one hypothesis which is interesting is that maybe the neutrinos are getting absorbed. So there's the Earth, and maybe the neutrinos that go through the Earth are actually getting absorbed by the Earth. So maybe that movie was right. Now, we know that that can't be true. Because we see, that would require a neutrino cross-section that's absurdly high. We would know about that. Unless the Earth is made out of some magic black hole-like material that eats up neutrinos. We would also know about that, by the way, because we have a feel of what the density distribution of the Earth is. So unless there's something very strange going on, it's very unlikely that the neutrinos are being absorbed. So what else could be going on? And there are only two other reasonable things I can think of. One is that the neutrinos are decaying. And then the other one is that they're changing flavor. And again, the idea is we're looking for either muon neutrinos or electron neutrinos. So if somehow they were converting into tau neutrinos, that could explain all these data. And one thing that people like to talk about is that if you are now giving the neutrinos a property that tells them that they're allowed to do something, but they have to do it as a function of time. That means that neutrinos that only travel a short distance don't get to do this, whatever this is. Then you can convince yourself that neutrinos have mass. Okay, why is that? Because whatever it is that they're doing depends on a certain amount of time. And one thing you want to remind yourself of is that only massive particles know about time. Massless particles do not know that time exists. As far as a massless particle is concerned, everything is instantaneous. Everything just happens. They don't have a concept of time. They don't have an internal clock. So if the neutrinos are doing something, and that something depends on how far they've traveled, that means that they know about time. That means that they have mass. Or Lorentz invariance is wrong. One or the other. And so that's where we were. And these are these very, very impressive atmospheric neutrino data that also have gotten the Nobel Prize for the Supercamioconda experiment. And again, they all have to do with telling us, and again, we learned a lot more after this, that neutrinos can change flavor as a function of distance and as a function of energy as well. Okay? So is this kind of clear? Because now we want to try to explain how this happens. Let me make sure. No. Okay. So in the next 5 minutes, I'm just going to set up the hypothesis that we're going to try to explore, which is asking what happens if the neutrinos have mass. And this is the stuff that's probably more familiar to people. So again, we want to take this picture here, and we want to violate some hypothesis like this one. And that will allow us to violate this other hypothesis here as well. So we want to talk about mass-induced flavor oscillations. So let's ask the question, what happens if the neutrinos have mass? So the hypothesis we're going to make is that neutrinos now have mass. And that means that there's a neutrino that I'll call neutrino number 1, which has mass m1. Then there's neutrino number 2, that has mass m2, and so on and so forth. So if you raise the hypothesis that neutrinos have mass, then there are a bunch of neutrino states that you can label according to mass. Okay? Of course, we also have the nu e, the nu mu, and the nu tau. These are what we call the interaction eigenstates. These are the neutrinos that you produce when you have a weak interaction. So the question then becomes, which one of these is the nu e, the nu mu, and the nu tau? And the answer is it doesn't have to be any of them. But what you know for sure is that the electron neutrino is a linear combination of neutrinos with a well-defined mass, right? And the muon neutrino is also a linear combination of neutrinos with a well-defined mass. And the tau neutrino is also a linear combination of neutrinos with a well-defined mass. Okay, just from basic quantum mechanics. That's the best you can do. And of course, you know that the electron neutrino state is orthogonal to the muon neutrino state, and that the muon neutrino state is orthogonal to the tau neutrino state. That means that they're different states, right? So this means that these combinations of numbers over here can be organized into a unitary matrix. So we like to write it this way, where alpha equals e mu tau, I equals 1, 2, 3, and this u alpha I, that's a unitary mixing matrix. Okay? And what I want to show you on Monday is that just by raising this hypothesis, you can explain all the data. Now, before I do that, you had a series of lectures on mostly quark flavor physics. So you've heard about things like the CKM matrix and so on. Let me just tell you very quickly that this is exactly the same hypothesis that happens in the quark sector. Now, we use very different language to talk about neutrinos. And that's for phenomenological reasons. But the physics is the same. You know, when we say that the electron neutrino is a combination of neutrinos with a well-defined mass, and so on and so forth, you're allowed to ask, you know, in the quark sector, what's the electron neutrino equivalent object in the quark sector? And what's interesting is there isn't one. There's no particle that does that. If you learn particle physics in a certain way, you learn about these states in the quark sector, and they're called the D prime, the S prime, and the B prime. Nobody remembers them. Okay? But the idea is very, very simple. Let me do it over here. What you're really doing is, first of all, you have to identify who are your real particles. Okay? Real particles are things that have a well-defined mass. So in the quark sector, you know, that's the up, charm, top. Then there's the down, strange, and bottom. In the lepton sector, we choose that to be the electron, the muon, and the tau. And then now I just told you the particles that have a well-defined mass are the nu 1, the nu 2, and the nu 3. There is no such thing as an electron neutrino. It doesn't exist. Okay? But the weak interactions, here's a W boson, and here's, say, the top quark. So we know that we can either get a bottom quark, a strange quark, or a down quark here. And this coefficient that comes on with this Feynman diagram is the entry of the CKM matrix, right? U, I, U, T, alpha, where alpha is B, S, or D. Okay? The exact same thing happens in the lepton sector, except that we do a couple of things differently. The most important thing that's different is that in the quark sector, we like to keep the up-type quarks the same, and then we make the coupling to the BD and S be the thing that's screwed up. Language-wise, it clearly doesn't matter. You can do whatever you want. In the lepton sector, we do it the other way around. The E, mu, and tau, they're actually the down type things. But the idea is, of course, here's a W boson. I better put a bar here. Okay. And the W boson goes into, say, an electron, and then it goes into either a neutrino number 1 or a neutrino number 2 or a neutrino number 3. And this coefficient here, then, is this UEI. Okay, that's the element of the neutrino mixing matrix. Okay, so you see that the physics is exactly the same, at least from a very microscopic physics point of view. The consequences turn out to be very, very different, especially in the way that we talk about things. And the main reason is the fact that the neutrino masses are really small. Okay, because neutrino masses are really small, you have this phenomenon of neutrino oscillations, which I'll talk about on Monday, that we do not have in the quark sector. And I'll try to convince you of that, at least in words. Okay? So again, this is the picture that you want to have in mind. It's exactly the same, except that from a language point of view, we like to talk about this electron neutrino, muon neutrino, and tau neutrino. They're not particles that exist, but they are a linear combination of things that you get when you have a charge current interaction with either an electron charged lepton or a muon charged lepton or a tau charged lepton. Okay, so that's what I think we'll start on Monday. Okay. Oh, I have more time. Wait, stop. I got the timing wrong. I have 10 more minutes, right? Oh, that's bad for you. Okay. Because I somehow I thought we were done at 10. Okay, so don't clap, just remove that clap. Okay, so let's talk about what happens here. Okay, and let me just set it up. I think there's enough time to do that. Okay, so now we have this picture, so let's keep that in mind. But now let's talk about this again as well, okay? So what we care about now is, so what does it mean to be a particle with a well-defined mass? Okay? So if you're a particle with a well-defined mass, from a quantum mechanics point of view, it means that you are an eigenstate of the free particle Hamiltonian. So if you're a free particle and you have a well-defined mass, you are an eigenstate of the free particle Hamiltonian. This means, oh, here's one, that if you have, say, a neutrino number 1 state, so you have a 1 neutrino state at rest, and you ask how does this wave function evolve as a function of time, it picks up a phase. And this is what it means to be a neutrino with a well-defined mass. And that's what it means to be an eigenstate of the Hamiltonian. Okay? Now, what happens then if you don't have one of those things, but you have a linear superposition of those things? So let's say you have the electron neutrino. And to make life easy, let's pretend that there are only 2 neutrinos. So the electron neutrino state is going to be a linear combination of neutrino number 1 and neutrino number 2, which I'll write as cosine of theta nu 1 plus sine of theta nu 2. And for completeness, we can write the muon neutrino state. And the muon neutrino state is also a linear combination of nu 1 and nu 2, but it's a linear combination that's orthogonal to that one. Let me stop and say some obvious things. We know that this is some coefficient that I don't know. This is some other coefficient that I don't know. But I know that the sums of the squares of these coefficients is 1. That's why I call them sine theta and cosine of theta. Again, this is a coefficient I don't know. This is another coefficient I don't know. Again, I'll call them sine theta and cosine of theta. And I know that this coefficient times that one plus this coefficient times that one is 0, because the muon neutrino state and the electron neutrino states are different states. They're orthogonal states in my quantum mechanics, Hilbert space. Okay? So that's why we are allowed to parameterize things in this way. If you don't like it, you can use A, B, C, and D with a bunch of constraints. Yeah. That's an excellent question. The answer is I can add phases here as much as I want. And then you have to ask the complicated question of, are any of those phases physical? And it turns out that for the types of measurements we can perform, none of them are. So that's why we don't add any e to the I thetas here. Oh, I apologize. So so what I said is still correct. This is the electron neutrino state. This is the muon neutrino state. We will then talk about what happens as this state develops as a function of time. Sorry, good. So thank you. That's a good question. But again, there are lots of other questions associated to parametrizing this. And they have to do with, can I add complex phases here? And the answer is yes. And then you can ask, why didn't you do that? Because they're not physical. There are all kinds of fun questions. One is, there's a minus sign here. Is that minus sign physical? It's not. I could have put the minus sign over here or anywhere else, and the physics would have been the same. So that gives you some hints about parametrizing this phenomenon. Okay? So this is the electron neutrino state. This is the muon neutrino state. Now you can ask, how do these states evolve as a function of time? And that's what you're asking. So, as a function of time, again, if we were living in a world where these neutrinos were produced at rest, and we've never been able to do that. Actually, we probably did, but we don't know how to detect neutrinos at rest. The cross-section is just awfully small. Okay? So this neutrino, as a function of time, looks like, so imagine that you started off with this one. So as a function of time, it just picks up a phase for the new one component, and a different phase for the new 2 component. Okay? And that's what this phenomenon is all about, is the fact that you started out with an electron neutrino. Because the different components acquire different phases, this is no longer proportional to the electron neutrino state. Or saying this in other words, the electron neutrino state is not an eigenstate of the Hamiltonian. Now, this is very, very simple physics. This is a 2-level system that you learn in undergraduate quantum mechanics, hopefully. Okay? Now, since I still have 5 minutes, which is great, I can finish this off by reminding ourselves that now everything is going to be relativistic. So let's allow the neutrino to also propagate. So the neutrinos are going to be plane waves. So the relativistic equivalent of this term here says that your neutrino state as a function of x and t looks like cosine of theta e to the minus I p1x nu 1, and then sine of theta e to the minus I p2x nu 2. This is one plane wave. This is the other plane wave. And x, of course, is just the tx4 vector. Okay, so I guess I can put mu's here just to make it look nice. Okay, so finally, so the other thing I want to say is we can talk a lot more about whether any of this makes sense or not. But we're using what's called the plane wave approximation, which is tricky, but it works. So that's what we're doing. Okay, so just to finish this off, we are now going to make what's called the ultra-relativistic approximation. So that means that for neutrinos, time is the same as how long they've traveled. Okay, so they travel at the speed of light. So that means that if you look at these phase factors here, they are very, very close to being 0. Okay, except that they depend on the difference between the energy and the momentum. Okay, so let me calculate the difference between the energy and momentum in this way. So I know how to calculate this. This is E squared minus P squared. That's equal to M squared. That means that the difference between the energy and the momentum is M1 squared over the sum of the energy and the momentum. Now, in the ultra-relativistic regime, the energy and the momentum are about the same. Okay, so in this approximation, my neutrino at a certain point L, a certain distance L from my production point, looks like e to the minus I m1 squared over 2e times L, neutrino number 1, cosine of theta, which I forgot. And then e to the minus I m2 squared over 2e L nu2 sine theta. Okay? So if I make these approximations here, then my state looks like that. Now let's calculate something. So let's calculate what's the probability that this object here, when it hits something, produces an electron. Okay? That's just this thing here. So I can calculate this bracket here. I get something that goes like a cosine squared theta e to the minus I m1 squared over 2e times L plus sine squared theta e to the minus I m2 squared over 2 times L, 2e, sorry. So this is the amplitude for having an electron neutrino be born somewhere, propagate some distance L, and then be detected as an electron neutrino. So the probability is this thing squared. So we can calculate that. So one easy way to do this is to take this phase factor, pull it out, and then the square of that is 1. Here you get the difference of the phase factors. So you get cosine to the 4th theta from the square of this, plus sine to the 4th theta from the square of that. Then you have the interference term. You get cosine squared theta, sine squared theta. Then you get, remember, the difference between those two phases here, plus the complex conjugate of that. That looks like 2 times cosine of delta m squared L over 2e, where delta m squared is m2 squared minus m1 squared. Okay? So does everybody see all of that? So let me move over here. So we can simplify that. So we have cosine to the 4th plus sine to the 4th. I can write that as cosine squared plus sine squared squared. And then I have to subtract out cosine squared theta, sine squared theta, the cross term. And then I have plus 2 cosine squared theta, sine squared theta, cosine of delta m squared L over 2e. I can do better. So cosine squared plus sine squared is 1 minus 2 cosine squared theta, sine squared theta, 1 minus cosine of delta m squared L over 2e, which then finally looks like this is 1 minus cosine of theta. That's equal to 2 times sine squared of theta over 2. So it's 1 minus 4 sine squared theta, cosine squared theta, sine squared delta m squared L over 4e. So what we learned at the end of the day is, so let me do it over here. That if you're born as an electron neutrino and you propagate a certain distance L and you're detected as an electron neutrino as a function of L, that looks like 1 minus. So this is a 4 sine squared theta, cosine squared theta. This is a sine squared of 2 theta. And then this is sine squared of delta m squared, L over 4E. Okay, so now that we've learned this, we know that it's possible to be born an electron neutrino and be detected as an electron neutrino with less than 100% probability. Yeah? Mm-hmm. Absolutely, yeah. This is a... yeah, absolutely. So that's the really exciting question that we will not talk about unless we want to talk about it in the discussion. But I'll tell you a little bit more. So what you're saying is completely correct, right? If you remember the language in the quark sector, you know, the top quark is produced either with a B quark or a strange quark or a down quark. It's not produced with a linear combination of those things. Why not? Okay, so why isn't it? And the answer is it is, kind of. But that somehow the system loses that information very quickly. So the system loses coherence very quickly. That's easy to understand. So imagine that you have, and again, if you give me 5 minutes, I can give you some examples. So imagine you have a D meson, you know, it's a charm meson, that decays into either a pion or a kaon. So the proper language for that really should be that it decays into a linear combination of a pion and a kaon. But then you're going to say, but wait, won't the system know whether it's a pion or a kaon? I mean, I can measure a bunch of other stuff to determine whether this other object that was produced was a pion or a kaon. So the pion-kaon quantum mechanical uncertainty, you know, this dichotomy gets broken up very quickly because the rest of the system knows whether I've produced a pion or a kaon. One big hint is that the pion and the kaon have very different masses, or they decay with very, very different lifetimes. So that means that in some sense, and this is with many quotes, the right language is you do get a superposition of all these states, but that your system, if you want, collapses the wave function very quickly into one of these mass eigenstates. Okay? So does this make sense? And this is so fast that we never talk about it. We just say that this is what happens, you know, that there's some probability that you get a certain meson and a different probability that you get a different meson. So the question is, for neutrinos, is it possible to know which mass eigenstate you've produced? And if the answer is yes, then all of this is wrong. Okay? If the answer were yes, so if the neutrino system is not coherent, so basically the key point is, can I describe the neutrino that comes out of, say, pion decay as a coherent linear superposition of neutrinos with a well-defined mass? If the answer is I cannot do that, then neutrino oscillations don't happen. Then what you've said is correctly, is that you either get a new 1 or a new 2 or a new 3. Nothing changes as a function of baseline. You still get flavor change, because the new 1, when it hits something, also has a non-zero probability of being a muon, but you don't get the oscillations. You don't get the stuff that does that. So the oscillations are really just from the coherence part. Yeah?
So you're saying if I could measure the electron recoil perfectly,
that's exactly correct. If you could measure it, and again, this is not a could of the type, can I be a very clever experimentalist and do this? It's a could of the type, the quantum mechanics uncertainty principle prevents you from doing that type. So it has to be such that it is not possible, in principle, to know whether you have a new 1 or a new 2 or a new 3. If you're in that situation, then you can have neutrino oscillations. Now, there are all kinds of issues here. One thing that's very obvious is the neutrinos that have different masses which are produced, they come out with different energies, just from energy momentum conservation. So how can I be talking about interfering states that have different energies? That also sounds wrong, and it is wrong. So the question is, what you really have to keep in mind is that physics processes are messy. When I say that you produce a neutrino with a well-defined energy, that's not true. What you produce is sort of a neutrino wave packet that has a collection of energies and momenta. And it's that collection of energies and momenta which are allowed to do this. So if you want, what I should be doing is to say the neutrino that comes out is a linear superposition of neutrinos with all kinds of energies and momenta. They're described by a wave packet. And I'm just telling you how one component of that wave packet is changing as a function of time, or L. Okay? And as long as that plane wave approximation holds, everything is good. And the question you have to ask yourself, is this what's happening in the experiment? And the answer is yes. And why? Because the neutrino masses are really small. There's no other reason. That's the only reason. No, it's because the masses are small compared with the typical energies of the process that you're talking about. So that's really important. And you can ask interesting questions like, imagine you invent a new neutrino that's very heavy or much heavier. Does that guy decohere quickly? A different question is, imagine you have a neutrino produced in a supernova, very, very far away. Do these guys oscillate or do they decohere? And there are decohering phenomena like the velocities of the different components of your wave packet are different. So they physically space out, they separate out in space. So that means that at some point your wave packet is split up into different components and then they no longer oscillate. A fun question to ask is, can I observe any of this? And we don't know how to do it. We cannot think of an experiment that we could do that could see any of these losing coherence phenomena, just because of the fact that the numbers are very weird. The numbers are always such that we are either in this great coherent regime, or we are in this very, very uncoherent regime. And before we can get to see the transition, our experiments peter out, and they kind of throw away all of the interference information by themselves, way before quantum mechanics will do it by itself. So that's kind of the gist of that.
So when the universe is spinning.
Yeah.
I suggest that let's take a
Okay. Good. Mm-hmm.
So when the universe expands, you can have like the super cool neutrino.
Oh yeah, the universe is a different story. Yeah. So the universe is. We're very, very confident that the best way to describe the neutrinos in the universe is a thermal bath of neutrinos with well-defined mass that are completely incoherent.